massive object. What's interesting about gravity, which is kind of different than other forces, is it's only, at least as far as we know, it's only attractive. Like electrostatic force, like protons, electrons, we know that if you have the same particle, right, in chemistry, those repel, opposite charges attract. With gravity, we only know about attraction. So, and I don't know if we figure out what antimatter is at some point, or anti-mass, or something will have some kind of repulsive gravitational force, who knows. But gravity is only attracted between two massive objects, and it goes towards the center of those objects. Now, so what that means in reality is that between me and this hook, there's a force of gravity. But why doesn't this hook fly on my head all the time? Why does it just sit there and stare at me, mocking me?
Because you're not that. You're not going to have a lot of mass.
Thank you. But why does that matter? Good. The Earth has a mass like 10 to the 24th kilograms. I have a mass of like 10 times 10 to the 2 kilograms. And so the force between this hook and the Earth is substantially larger than the force between me and the hook. But they have in lab, they've shown that there is a gravitational force between all objects, but the force between this and the Earth is so much larger that it gets trumped by my menial force on that hook. So everything has gravitational force between it. And so that's what gravity is.
But wouldn't there be three objects interacting if those hook onto your face? Because it would be you and the hook.
Well, there's two different. There's the force between me and the hook, and the force between the hook and the Earth. There's two different forces there. Yeah, that's a good point. And that's the point of the definition is that that's not just one big force. There's 1,000 forces of gravity going on all the time around us. That's what they talk about. That Yoda talks about, right? And so that's good. So now we have this puck. We said the puck's sitting on the desk, right? Is there anything else acting on this puck? Is that the only force on the puck? No. How do you know that's not the only force on the puck? Right. So which way does the puck want to go right now?
Down.
Down. So the puck does not go down, obviously.
The desk is putting force on.
What?
The desk is putting force on.
Great. The desk is putting force on. So we're going to do this chapter. We're going to draw a lot of what we call force diagrams. And we're going to try and diagram the forces on objects. So let's try and do that right now. Let's draw a force diagram for the forces on this puck. Let's use some color other than orange. So all our force diagrams, we're not going to try and draw the objects because it seems very complicated. We use that, I think in the first chapter it discussed using like dots for all of our drawings. So I forget what that's called, but I don't remember. Most of it was like the particle model system or some weird name like that. We're basically going to draw everything as if it were a dot. So here's my air puck. Whee! What forces are on this air puck right now? What's going to gravity? Good. So gravity is going to point down. So I'm going to start here and draw down. We're going to label. That's going to be a little too long. I need to draw mine shorter. I'm going to run out of room. There you go. We're going to label all of our force arrows. Because remember, force is a vector, so we draw an arrow with it. We're going to label all of these force vectors with something we would call on by notation, like the word on, O-N, the word D-Y, by, on by notation. And you're going to have to do it every time or two, otherwise, if you want to get full credit on things. I know some of you don't like to do this kind of stuff, but you're going to have to. So there you go. So the force of gravity on FG, force of gravity on what? What's this acting on? What's the gravity here acting on per se? Puck. So on the puck. Now gravity isn't actually acting on anything. What specifically is causing the gravitational pull on the puck? The force. What's the force being caused by? The mass of the Earth. So it's on the puck by the Earth. Capital E, not lowercase, Earth. It's not dirt like, Earth on the ground dirt. It's Earth, the whole flipping thing is pulling that puck down right towards the center. Like that. So we do force of gravity on the puck by the Earth. That's your on by notation for that. Questions?
Every time you do that?
Yes. It's very annoying. But it's good for you. I promise it'll help you. Ever since I started doing it that way, it's been a lot less mistakes on things. Won't do that all year, just probably for the next couple of weeks. We'll do that long way. So good. So Jason tells me that this table is pushing up on this puck. Anyone disagree with Jason? Good. Very good job, Jason. Now, we're going to name that force specifically here. We're going to call that the normal force, which might seem like an odd name, and maybe it is, but that's what we call it, the normal force. So the normal force, this is the tough one to define. We'll call it F with a little n after it, subscripted. This. So the normal force, we'll call it a reactionary force when two surfaces are in contact. That maybe it doesn't make any sense what that means, but we'll try and talk about how we actually use that normal force in practice. So the normal force we'll discuss. Anyone know what does the word normal mean besides like regular? It means in mathematical context it has a meaning. Anyone know what that is? You draw a normal line to something. Perpendicular, good. A normal means perpendicular in math land. So a normal force is always going to be perpendicular to the surface that it's coming from here. So in this case, which way would normal force point, do you think? Straight up, because here's the table. Normal force is going to come right out of it at a 90-degree angle, like that. So I'm going to draw that as an up line right here, like that. So touch this thing. And I'll write F with a little N after it. On what? On the puck. By what?
The desk.
The desk or table. Very good. And so the point here is that, and I don't remember this period, last period now, but someone said something like gravity acts on the puck. Gravity doesn't do anything. Gravity is the name of a force that the Earth provides on something. And so we really want to be clear here what's causing the force. As we get into more complex systems, we have to know what force is causing what and how those are all interacting together. And so that's my force diagram, almost done with it. And again, this normal force, if this is the desk or table, here is your perpendicular angle. Questions so far? Now, how do we think those two lines are related to each other? They're probably going to be the same size. And why is that? Just logically thinking, if this puck is going to be stationary, then those two forces are probably going to be equal. We would think if they weren't the same size, then the puck would probably be doing something besides sitting still. That's a force diagram. Questions, comments, concerns? All right. So how do you think I can make this puck move? Is it possible? Is that puck going to stay there forever? Is it glued to the table, or how can I make it move? I can push it. That's awesome. Good. So I push the puck, which would be me applying a force on the puck. Where a force is directed between two objects. So I'm pushing the puck. What do you think I should call that force that I just applied on the puck?
Pushing force.
Pushing force? Not. We couldn't call it normal. That's not always going to be perpendicular. We like to reserve normal just for like tables holding things up, really. Pushing force would be fine. We're going to be a little more generic. I'm just going to call that an applied force. Pretty simple name there. Where's my mouse? There it is. Applied force, again, I find this one, again, tough to define, but I'll give it a shot here. An applied force, I'll turn lights off in a second here, F with a little A after it. Say is a contact force between, I don't know, two, I guess that's fine. Contact force between two objects. That's hard to define. You kind of know it when you see it. Contact force will usually be a push or a pull. You're just, touching the object. But the key to applied force is there's a contact involved. Because you can also have field force like gravity, where really gravity happens whether the Earth touches you or not. And contact force, you have to have contact. So really, when we go through the rest of our forces, if it doesn't fit under any other category label, it's probably an applied force. So if you did something to an object, it's an applied force. Again, the names aren't real important here, but it's sometimes helpful if we can label things. So I applied a force in the puck and it moved. Very good. So let's look at this more thoroughly. So I hit the puck, and we said it moved, right? Yay. Can be more specific about the motion of the puck. Not just saying it moved, was there anything more detailed about it besides just moving? It moved right, okay, so that's true, it moved to the right, but yes?
Slows down after the initial push.
But what about before it slowed down?
Friction.
That's why it slowed down. What about before it slowed down? What did it have to do first? Joe? It had to accelerate. Good. So when I initially hit the puck, it accelerated. It sped up. Agreed? Yes, no?
Yes.
Yes. So when I applied this initial force, it sped up. If I kept applying the same initial force the whole time, it would keep speeding up the whole way across the desk if I kept applying a force. Agreed? Now, why do we say that puck, why is the puck there not move?
There's two equal forces.
Two equal forces. The forces in this diagram were what we'll call balanced, right? What about when I whacked it? Why did it accelerate to the right? Unbalanced force. Very good. So that's the next thing we need to write down. And that is that, and this is, if nothing else, the most important thing today, lots of important things, but if nothing else, unbalanced forces cause what?
Movement.
Acceleration. We want to be a little more detailed than movement. So it's unbalanced forces causes acceleration. Or we could say, in some cases, it might be easier to say, instead of acceleration, it might say a change in motion. Could sometimes be an acceptable alternative. But it's critical to note the motion is changing when the force is unbalanced. If everything's balanced, then the force is not going to, say it again. If everything's balanced, then the motion is going to be constant in terms of its velocity. Okay, so unbalanced forces cause acceleration. Questions about that? Good. So I thwacked the puck. It moved. Audrey, what happened then? You said?